Ora si registrerà la conferenza.
With no video, but okay. No, but it's only the webcam. The slide should be visible, and the seminar will be given by Professor Imre Salma from the University of Budapest, that has a long experience on different aspects of atmospheric aerosol, and his recent interests are specifically on the study of urban operation and the relationship between quality and depth, with specific focus on oxidative potential and cellular toxicity. So just we can, I think we can start, and Imre, the floor is yours.
Is it fine? Okay, thank you very much. Good morning, everybody. First of all, I would like to express my thanks to Professor Contini Daniel, who for hosting me here and for showing me around his very valuable network, very comprehensive network, and also for the discussions we have started yesterday, and hopefully we will continue on oxidative potential, because everything I saw confirms that you have been and will keeping going on in approaching and achieving very considerable success. So I will talk about atmospheric nucleation and on its effect.
You have to share the screen.
Share the screen here.
Okay. Okay, can you see the screen now?
Vedete tutti lo schermo condiviso?
Come si fa a chiudere questo? No, credo questa chiude tutto. Ok, they see the screen. Questa? No.
Si vede.
Perfetto, grazie. Yeah, okay.
So I will be talking about atmospheric nucleation and on its effect. The emphasis will be on the urban environment. So there is no story of atmospheric nucleation, but urban nucleation is struck into the focus recently. I don't think I have to talk about the mechanism of atmospheric nucleation and its causes, but I would like to start with a little comment, with a note, which seems to be minor, but I think it is very important to pay attention to. Everybody who
sorry, just the okay.
Okay. Everybody who is involved in atmospheric chemistry and physics can be compared to a tailor in the fairy tale about the moon and the tailor. I don't know whether you have the fairy tale in Italy as well. Okay, the moon would like to have a dress, and the tailor takes measures the dimensions of the visible moon and prepares the dress, beautiful dress. But by the time the dress is ready, the moon is already in a different shape, and the dress doesn't suit to him. And it is repeated. So the tailor needs at least 2 times 28 days to recognize what is going on. But atmospheric chemists and physicists is even in a more difficult situation, because there are chemical processes, physical processes, meteorological processes, biological processes going on in the atmosphere. They are interrelated. There is interaction between those processes. Then you have some phenomena which are repeated or in a daily base, weekly base, yearly base, or quasi-periodical, and they are then unpredictable events or fluctuations which create the atmospheric situation. So when we measure, we repeat the measurements, it could be considered different from the first measurement point, and therefore it is very difficult to emphasize the importance of long-term measurements. And in these measurement stations or groups are very important. This is the picture of Budapest. Here you see the Danube, and this is the campus of my university. And on the second floor, we have a measurement station, which is called Budapest Platform for Aerosol Research Training. You can also
We are typing.
Sorry.
no problem at all. I'm glad that so many came. So we have the measurement laboratory, Budapest Aerosol Research and Training Laboratory, located in the city center. As a matter of fact, the city center is here. It ends at this bridge. But there is very often a wind channel above the Danube, and it brings in a very well mixed air, which characterizes the average air in the city center. So we are not interested in a particular site or a crossroad, but we are interested in the general air of the city center. And you can see the situation right now. We have a differential mobility particle sizer here. Here is a cloud condensation particle counter, double column, with a CPC. It's an FDMS term for measuring the mass if we need it for the mass balance. And right now we have a photoacoustic spectrometer here also performing measurements related to atmospheric nucleation. And then we have some samples. So these are only the online instruments which are there permanently. And if we do sampling, usually we do it in campaigns, and then we put the samples also into the container. The long-term measurements have several consequences, and the variability in atmospheric chemistry and physics, several consequences. One of them that the statistics which describe the experimental data are not normal and are not even Poissonian distributed, but they are log normally distributed. And log normal distribution has very nice properties which we can take advantage of. Secondly, that the long-term measurements. This is absolutely needed to have long measurements to arrive at reliable conclusions, reliable results. And the third consequence is that if you find out some interesting point or consequences, then you need to show it also how is it at other sites in the region or in Europe or even globally. So therefore we need a very close cooperation between those groups, and I think that from this point of view, although Budapest and Lecce are far from each other, but to have a total coverage at different altitude and regional environments, this would be a very good occasion also to have a closer cooperation in this field as well. Just to demonstrate the importance of long-term measurements. So we started in 2008, and since then we have finished 11 years in the city center, so year 1, and all the others are in the city center, and year 2 was in the near city background. It is a forested site close to Budapest or at the border of the Budapest. And here are the relative occurrence frequencies, which show that in a month, for instance, in December, this fraction of the day were associated with nucleation. So you have the yearly distribution of the monthly occurrence frequencies. And if you look at the column pictures, for the first time you don't see a mess, because there are some distributions which remind each other. For instance, this is similar to this and this and this, but then this is completely different. This is similar to this. This is completely an outlier. This is also not very distribution with a very evident feature. But if you sum the years up, so you make the average of the all years, then you obtain a distribution which already has several features. Okay, so this is the average average distribution of occurrence frequencies, and you will see that there are some elements of the individual distributions which are repeated. And now I would like to talk more about the average distribution. It has a minimum in winter, in December and January. Imagine that there were some Januaries when we did not obtain a single nucleation. Okay, and the first year when we started was among them. So in January we started in December. There were a few nucleations, and then in January nothing. Then I told to my PhD student, okay, we will go to conference and we will say that there is nothing in Budapest. But later on, fortunately, the spring arrived and the number of nucleations started. And finally, we have occurrence frequency of 20%, which means that every fifth day on a yearly base, there is a nucleation. And this is somewhat surprising because it is not at all less than at other cleaner and more distant sites. So it's about the average frequencies between 10 and 13. So we are just in the middle. So I would like to discuss the yearly occurrence frequency, and also you can see that there is a peak in spring. So I would like to come back to this peak and to have somewhat better. So in the very beginning there was an imagination that nucleation occurs only in very clean environments, because the rival process to nucleation is the condensation. So if you have lots of pre-existing particles and there is condensation on the particles which quenches out the nucleation. And this was one of the contour plots which I showed in a conference, and you see that the air is polluted, the red color dominates everywhere, and in spite of that, you have the banana curve, the purple banana curve. So even when the air is polluted, you can have nucleation under some circumstances. But what are those conditions? So we try to evaluate the pairwise correlation between the environmental conditions, properties, parameters, and the occurrence frequency. Now I would like to show you just two: the sulfuric acid concentration, the distributions, and you can see, if you remember the first slides, that there is no real correlation. There is some influence. You can see that there is sometimes there is an indication of the spring peak, but it is not very evident. So we could not conclude that the sulfur dioxide, the sulfuric acid, influences the nucleation. Then we looked at the variation, also no real association. We looked at the temperature, and not only at their absolute values, but also at their relative changes, which is called standardized anomaly. So what is the difference of the actual months with respect to the overall average? About, I think it was 7 years already at that time. We could not figure out. So we could not find what is the driving parameter in nucleation in Budapest, and we concluded that it is not possible to show because there is multifactorial effect. So many things play a role at a time, and as a consequence there is nucleation or no nucleation. And coming back for the very beginning ideas that the condensation sink limits the nucleation. So there is a critical value above which you won't find nucleation because the condensation process takes over and quenches the nucleation. So we also had some indication that there is 0.02 second minus square when after this point we did not obtain nucleation. But we recognize and realize that the growth rates increases with the condensation sink. And you should pay attention, this is logarithmic scale, so visually it is not a big increase. In reality, it is much important than it seems. And then started to evaluate somewhat this and also follow the theoretical works which already existed on the survival probability of particles. So what is the survival probability of particles in a diameter of 2 nanometers as they are born until a certain range where you start measuring? So we start measuring at 6 nanometers. So what is the probability that the particles reach from 2 to 6 nanometers? Okay, and there is a nice theoretical work from existing, so we followed up, but we could not find a real effect. So here is this parameter which is included in the survival probability, and here is the formation rate, and these are the theoretical lines. So they are not in contradiction, but as a matter of fact, they do not confirm that the whole process is governed by the survival probability, and this is so because the 6 nanometers also could be seen as a low enough diameter, but for some processes it is not. So at 6 nanometer we obtained that a very high number of particles survive. So 75% of particles survive, and this is too much already, which could cause a change or difference in the curves. The other element of the occurrence distribution is the spring peak, and this is very often repeated at other sites. So we started to evaluate why the spring peak appears, and we thought that it must be very general. It is at many mid-latitude areas. So here is Budapest, and we took a 100-kilometer diameter circle around Budapest, and from the satellite data and the surface coverage, we could figure out which spots are occupied by vegetation, forest, agricultural land, and we refined the normalized difference vegetation index, which is called NDVI, from the satellite MODIS, which flies from Earth's Terra. And this satellite product, which represents the difference in the near-infrared reflectance to the red reflectance to their sum, is proportional to chlorophyll. So we have a product which shows you the coverage of the chlorophyll on the surface. And we looked at the time series of this NDVI product. This is winter, this is spring, and we took the difference between the maximum and the minimum and took 20% of this, and these were then related or taken as the start of the vegetation spring. And finally, we correlated the vegetation spring to the nucleation spring. Okay, here you see the start of the spring in days, vegetation spring, and start of the new particle formation peak again. And you see that there is nice correlation, except for 1 year, year 2, which was in a forest. And this is known that the vegetation spring is delayed. Okay, the forest very often has a name black forest. dark forest, okay? Because there is less radiation, and therefore the vegetation spring arrives about 2 weeks later, then on a grassland, or then on an agricultural open land. And if you take into consideration these 2 weeks, then this black dot is very nicely on the curve again. So this was excluded from the regression, but others were very nice, and the coefficient of regression is also, I would say, very good, taking into account the uncertainties of the results. So we could show that there is a relationship between the vegetation, the emissions from the trees, and the nucleation, but I'm not claiming that this is the causal effect, because there could be some other, a third effect which govern both of them. Could be the sum of the radiative energy or something like that, but we could not go further, but at least we may say that the vegetation are in contact with atmospheric nucleation. Not only the growth, but the nucleation itself is also somehow influenced with the causes which also advance vegetation phenology, growth of vegetation. Another specialty of atmospheric nucleations in cities, that very often we have double onset or multiple onset, and then instead of a very narrow neck of the banana curve, we have a very broad neck. For instance, here you have 2 onsets. So this is the first and the second onset, and the banana curve is developed here. So we looked at the dynamic properties of the first and the second onset, and we could figure out that the first onset has a higher, smaller formation rate than the second onset, and also the growth rate for the first onset is smaller than for the second onset. Here are the ratios. Okay, 2.5 times more particles are produced with the second, and their growth ratio is also larger by 2.8 times. If we compare them, and also the timing is different. About 2 hours later, the second starts with a delay of 2 hours. And if we compare the 2 onsets with regional data, which come from Cape Pusta, and with the Budapest Center data, you see that this is characteristic more to the region, and this is characteristic to the city. So this is a combination of the regional nucleation and the urban nucleation. And the urban produces more particles than the regional one. Okay, so this is some combination of the 2 effects. I would like to show you also some comparison of our measured data to the cloud chamber data, which is in CERN. Okay, but it is a very nice place, and they evaluate the mechanism of several types of atmospheres. And in the very beginning, there were ideas about thermal nucleation, sulfuric acid, water vapor, and ammonia. And the curve shows you the nucleation rate in different sulfuric acid concentration within the chamber. But you see that the formation rates which we measured in the atmosphere were 3 orders of magnitude higher than they obtained in the chamber. And therefore, there was a need to extend the thermal nucleation, and it was finally extended with amines. Amines are more strong bases in the air than ammonia, and therefore we obtained already very close formation rates in the chamber to the ambient data. But we also did some measurements. You have all the instruments, the PSM, NIOSH, that you can measure nucleation rate at very small diameters, 1.8, 1.7. So here are these curves, which you can hear, at least the linear part of the curves. Here are the ambient measurements, and the yellow dots are the data for Budapest. So it is clear that DMS is there within the system, so it must be included. But if you look at the data as a whole, as a cloud, you see that the cloud is more on the left side of the red curve. So there could be something else involved in the atmospheric mechanism. Not only DMS, but something else. What is this? We don't know. We call it unknown player. That something is still there which influences the formation rate in nucleation. If I am talking about the atmospheric mechanism, I would like to mention that there are some parts on the Earth, especially the poles, Antarctica, where there is nucleation, although the concentration of sulfuric acid is extremely low because it is cold. So you don't have sulfuric acid in the air, but there is nucleation. Imagine that there is more nucleation in the Antarctica than in the Amazonia. Okay, so what drives the nucleation there? And it was known that at the seaside, especially in high altitudes, the iodine compounds play a role. So here you see, and this is, I don't know how it is in English, the brown algae. Brown algae, which during their metabolism, and especially when they die, emit lots of iodine compounds. So there was a hypothesis that on the very cold, on the pole areas, the nucleation is diverted not by sulfuric acid, but by the iodine compounds. And this was a breakthrough because before that, everybody told that there is only one mechanism, sulfuric acid, water, and amines ammonia. So this is the second plausible idea on the mechanism of nucleation, driven by iodine family. And this is a picture which I took in Galway. But of course, this is the idea, but you have to prove it. So there were very nice experiments in CERN, in cloud chamber again, showing the mass effect of the product of the molecular clusters. And this is the chemical characterization of the cluster. These purple lines are not important because this is chemical ionization. So these are related to an ionizing agent, the nitric acid ion. So these are not important, but these lines are very exciting because they show that there is iodine acid and iodine pentoxide. So there is a molecular cluster where instead of the sulfuric acid you have iodic acid, and instead of the bases you have iodine pentoxide, and they can even prove what is the sequence of the molecules. One iodine oxide, one iodic acid, iodine pentoxide, another iodine pentoxide, another iodic acid. So this was a proof that there is feasible nucleation in chamber. But how it is in the real environment? So there were some places in the world where iodine family concentrations were available, and you see first of all that the concentrations are higher at the sea coast and the northern sea coast, and they are less emphasized. And also one species, the iodic acid, completely is in larger abundance in continental territories. So this was a very, very nice experience, a very nice story, because if you have clouds, atmospheric nucleation normally leads to lots of clouds, and the structure of the clouds is changed. So, and normally the clouds shield the surface, and they have negative cooling effect. Okay, a negative climate forcing, except for the poles during the dark period, because there is no sunshine, but you have clouds, and there is reflection of the heat radiation back to the surface, and this could be caused by the poles are increasingly heated, and ice caps on the poles could be influenced by the clouds during the dark period. I would like to come back to the nucleation in Budapest, and another question is how big. So if there is a nucleation, how big is the nucleating cloud, if I may call it like that? And we are very lucky because we live, Lecce is beautiful, okay, but we live in a basin which is also not ugly, okay, and it is even very nice from the atmospheric chemistry and physics point of view. This is Carpathian Basin, okay, this is Carpathian Basin, 700, 900 kilometers in this direction, 400 kilometers in this direction, and we have continuous measurement in Budapest here, and there is in the regional background, most of the basin is plain, call it the Great Hungarian Plain, and on this plane, we had expenditure measurements at the Cape Pusta site, which used to be an INEP station. So we measured at both sides in parallel and compared the data and evaluated data and find out that if there is nucleation at one side, there is very often or almost every occasion nucleation also at the other side. And we looked at the shifted extremes. When the spring extreme was shifted in a bay, the other extreme was shifted in parallel. And also we looked at the air mass backward trajectories, and we recognized that this is a very advantageous property of the two sides, that there is a prevailing wind direction, northwest. So if there is a nucleation here, then it could be brought by advection to the other location. It's 80 kilometers in distance. But we recognized that the wind reached only 1/3 of the distance, and the nucleation at the other side already started. So taking all three together into account, we could conclude that atmospheric nucleation is a consistent and spatially coherent phenomenon in the Carpathian Basin. So if there is nucleation, there is nucleation all over the Carpathian Basin. It naturally doesn't mean that everywhere the nucleation starts at the same time, and if there is nucleation, that it is at all points, because there could be some local sources or local effects which promote or play against the nucleation or even quench the nucleation. So jokingly, I call sometimes that nucleation amoeba. Do you know the one cell animal amoeba which moves and extends and cools back? So there is nucleation amoeba in the Carpathian Basin. Anyway, the conclusion that this is a regional phenomenon also emphasizes the importance of our work. And this is demonstrated with the dynamic properties. When we did the work, we had 5 years of measurements. This was at the near city background, and this was at 5 years, and this is the average. And if we look, you can see that the nucleation normally starts at 9:15. It takes about 3 hours. It generates about 5 particles in a cubic centimeter in a second, and the growth rate of particles is around 7 nanometers in an hour. If you look at the regional, well, not at the city center, near city background, at the edge of the city, the nucleation starts 1 hour earlier. It takes about the same time and produces half of the particles, so it is less intensive, and the growth rate is comparable. 5 or 7 doesn't really make a big difference. When we looked at the seasonal dependency of the dynamic properties, then we obtained completely different curve than for the occurrence. So the properties, the dynamic properties, have maximum in summer. And perhaps this is more or less understandable because everything, I mean, the reactions, the chemical reactions in the atmospheric processes are temperature influenced. Until you have higher temperature, all the generation processes are faster. But this is also important to be aware that the occurrence and the properties are governed by different background processes. Another one information to recognize is that if you consider the nucleation takes 1 hour, then 1 hour is 360 seconds. Multiplied by 5 particles generated in a second, you obtain 18,000 particles, which means it is much larger than the concentration of normally existing particles. In Budapest, we have about 9 or 10,000 particles in a cubic centimeter. So if there is nucleation, it is increased at least twice. And we were to quantify this effect, and we introduced nucleation strength factor, which is the share of the particles generated by nucleation to the total number of existing particles. We can have the ratio of ultrafine particles to the regional particles during the nucleation days, and the same ratio during the non-nucleation days. So this ratio includes all sources, and this ratio includes all sources but nucleation. So the ratio specifies the contribution, and we can have 2 contributions. One is what is the increment on nucleation days. So you have a certain number of particles. If there is nucleation, what is the increment of the concentrations? And you see that in the near-city background, if there is nucleation, then the number of particles is increased by 2.3 times, which is considerable. Even in the city center, the increase is 1.6 on the days when you have nucleation. On a general day, of course, the contribution is much smaller. We call it general contribution of nucleation. About 30–40% of the existing particles are increased by 30–40%, and in the city center the increment is much less, around 30%. You know, Marco Kurmala, who is pioneer of the nucleation, is not very happy because he would like to have larger contribution, but of course I can do nothing else. I just would like to mention that in this regional nucleation, the particles from the previous days are considered as primary, and this is not completely true. So these data, the increments and the contributions, are very conservative estimates. So as a matter of fact, it could be somewhat higher. And we were to study this, refine the contributions, but it was not necessary because a new phenomenon was discovered, and this is called quiet nucleation. Quiet nucleation, and it also points to the importance of long data sets. Okay, when we make an average of the size distributions of the contour plots, but not a normal average, but on a normalized average. So each spectrum we divide by its largest point, but its maximum, and then you obtain size distributions which go from 0 to 1. And if made the averaging, then each distribution will have the same weight. Otherwise, if you normally average the distributions, the largest peaks have higher weight because of their content, and they completely wipe out the effects of the smaller distribution. So this is the averaged contour plot from 2008 to 2020. And you see a more clarified situation. Here we have a morning rush hour emissions, afternoon rush hour emission evening, and here we have around the noon a very nice banana curve. But if you do the same to non-nucleation days, so which were classified classically as non-nucleation days, we obtain this situation. You see the morning rush hours, you see the afternoon rush hours, which correspond to them, and you see a transition from the very small particles to larger. So there is, as a matter of fact, nucleation. Very weak nucleation, which are so weak that you cannot measure them because of the sensitivity of the instruments, because they are really so weak that it is not possible. But if you add up in a manner that every size distribution has the same weight, they show you a nucleation in the background. And this was already found speculatively by Estonian people, and they coined it as quiet nucleation. So we kept the name and started to quantify its effect. And it comes in the picture, what I mentioned in the very beginning, that you need collaboration. You have to prove that the effect is also at some other places. So finally, we did the same calculations for Hytia in Finland, on an Estonian rural site, and 2 sites in Budapest, the near city background, the city center. And we find out that the formation rates are decreasing in a monotonous manner. Okay, so in the city center there is much bigger difference between the classical nucleation and quiet nucleation. Okay, 16 times. But if you go to more anthropogenical, more influenced sites, the difference is less and less. You have to also take into account you have much more non-nucleation days than nucleation days. As I mentioned, 1/5 of days are nucleation and the rest 4/5 are non-nucleation days. So if you take this into account and you calculate the production rate, daily production rate for classical NPF events and classical NPF non-events, then you find out that, for instance, in the city center, about half of the particles could be generated by these quiet nucleation, which means that the estimations, which I gave, 30% plus something, could be immediately doubled. So we may say that atmospheric nucleation is the major source in the global atmosphere. In the situation in cities would be different. Nevertheless, at least 30% of all particles come from nucleation, and only the others mainly from cars. I would like to show you also an exciting example, which is now called decreasing mode diameter nucleation, that we quite often obtain banana curves which are not developed, but they have an arc size, arc type, arc shape. Here you see an arc shape, and since then we have even better pictures of the eye-shaped particles, and they represent about 4 or 5% of class A nucleation type. Okay, the quantified events which are belong to the best and nicest banana curve, 4 or 5% of those events have this arc type or arc shape. And this is the growth rate, and this represents the decrease rate, or it was called at the time shrinkage rate, but as I showed, it is not always shrinking. So nothing special. We compared it with some other parameters, atmospheric parameters, including meteorology and some aerosol properties, and figured out that for most of the cases, this shrinkage can be explained by meteorology, by changes in the meteorology. So if there is nucleation, then the growth starts. But during the growth, if something happens, for instance, change in relative humidity, change in temperature, change in radiation, then some of the components would evaporate. But it raises at least 2 questions. Normally, we assume that the chemical species which take part in the nucleation have very low volatility, like sulfuric acid, extremely low volatility organic vapors. How it comes that they evaporate? So this is not possible. You assume that they have low volatility, something changes and they evaporate. Nevertheless, also in the smoke chamber in CERN, they recognize that there are some other organics called highly oxygenated molecules, which play a role in the nucleation and growth, especially in the growth, and they are not necessarily all low volatility. So if there is evaporation, then it could or should involve holes. But I have to tell you that there were some archetype curves which we could not explain. For instance, there was one single curve during which the daily average temperature was -2 centigrade. So I cannot imagine that something evaporates from particles at -2 centigrades under atmospheric environment. So this is very unlikely. And therefore, a modeling study was completed with a Finnish group, where they showed that if the nucleating cloud is advanced, then and advected to other places, and during the advection, the conditions change, there could cause that seemingly the growth rate or the formation rate decrease. So this is not at all shrinkage, as we called it at that time. So this is an artifact of passing through a territory where the formation rate is decreased, and then you obtain the archetype curve. So it is not necessarily, or in some considerable cases, is not governed by meteorology, but by the nucleation dynamics itself. How those nucleated particles look like? So we collected individual particles on a 10 grid. Then you have a copper grid, and on the copper grid you have polycarbonate lace. So these are the lace wires, and on the laces, the lace is covered by amorph graphite to make it electrically conductive, and we collected particles by their electric charge, several kilovolts, on the laces. And several particles are there, several known particles there. This is, for instance, a soot aggregate. It has a fractal dimension. Then this is a sulfate particle with organic inclusions. And this is a very famous type of particles, so-called tar ball, which is everywhere, omnipotent everywhere, even under the ocean. And it is made almost exclusively of carbon. It is a product of biomass burning. Sometimes we have those small particles, which we call nanosoot particles, which means that only a few soot balls stick together. And if you are lucky enough, you can recognize the fractal shape of the particles, but more importantly, if the particle is at the edge of the lace, so there is no background after the particle, you can make a high resolution electron microscope image. For instance, this particle, it's made of 3 spherical soot balls. And these balls, you can see one is here, the second is here, and the third here, and you can see the internal structure. The graphene, these are cracked graphene layers, but you can see them, okay? You can see these cracks. So, but these particles are known. But we found some particles of similar size as nanosoot particles, but without structure. So they look homogeneous. And those particles were very small particles, 50, 20 nanometers. And we were to make an elemental map of them, whether we can see the sulfur and carbon. But unfortunately, those particles can withstand the vacuum in an electron microscope, but they cannot withstand the effect of the electron beam. So they just evaporated, and we did not obtain any signal. And when we compared the TEM transmission picture before and after the electron microscopy exposition or imaging, they disappeared. So they are volatile under that electron beam. The last thing I would like to mention is about the health effects of ultrafine nanoparticles and particle number concentrations in general. We have a very nice stochastic land deposition model called IDEAL. It has been developed for decades. It was developed as a joint project between the Central Research Physics in Budapest, it was my former workplace, and the University of Salzburg. Both the pioneers already went to pension, but their PhD students go on with that. And since I work there, I have very good contact with them. This model has three types of input parameters, morphometric parameters, regards the anatomy, the human anatomy. Okay, the lengths of the airways, the angles of the airways, angles toward the gravity, and they are included in the model. You can select adult male, adult female, or a 5-year-old child, and you have the morphometric data. And then the respiratory physiological parameters, we breathe differently. We breathe differently because of our gender. Okay, the male breathes more. Normally, the volume of the lung is about 5-6 liters, but we exchange only 0.5-0.6 liters at one breath. So very minor volume of the total volume is exchanged. And this is different for females and males. Also, the breathing frequency is different. Okay, females have more frequent, smaller breaths than males. And also this is completely different for child. So this is included also in the model. You can select whether you are to study the adult male or a 5-year-old child, and then the parameters go accordingly. But the third type of the parameters are side distributions and hygroscopic properties of particles. And this is which is accessible for us. So we can run the land deposition model, and all major deposition mechanisms are included: impaction, settling, gravitational settling, sedimentation, and diffusion. And we can even have randomly selected airways. So what is the parts of the particles in the land is selected stochastically, but the deposition in each airway is calculated in a deterministic manner. And even more, we can have healthy lung and compromised lung, for instance, with COPD disease or bronchitis, because the morphological parameters of the unhealthy lung are different. And then we run the model. This is a mathematical model, and we obtain different deposition fractions. The first is the deposition probability. So what is the probability that the particle which is inhaled will depend at a certain place of the airway? So this is the lung, this is the trachea, airway generation lung, then the main bronchi, then the bronchi and the alveolar region starts under here, and it ends about 27-28 generation because our lung is limited. Okay, the right lung is larger than the left lung because of our heart. So statistically, the end is not an absolute value, but it has some distribution. You can see that the distribution is quite large, especially if you compare it with the distribution of mass. A few percent of particles are deposited in each segment. And you can also see that something is strange, because the highest deposition probability is and heavy exercise, but then light exercise and sitting and sleeping are the 4 reference values which determine your breath frequency. Okay, so it says that when you sleep or sit or doing sitting activity, the deposition probability is smaller. So this is sitting, sleeping and sitting, but look, heavy exercise and light exercise are much larger. But this is only part of the groups. because this is the probability of depositing one single particle somewhere in your lung. But of course, if you breathe an ambient air, then the air has different concentrations. It also depends how many particles you inhale, and this is expressed by deposition rate. Deposition rate shows you again that particles are mostly deposited in the deep lung, and you have then a nice monotonically increase from sleeping, sitting, light exercise, and heavy exercise. Does it mean that I? Okay, there is a common misunderstanding that we say that the smaller the particle, they penetrate into more deep into the lung. It's not completely different because completely correct, because each particle has a probability of deposition anywhere in the lung. Nevertheless, we can see that if you increase the physical exercise, the maximum range where the particles are deposited is increased. Okay, but there is another aspect that the surface area where the particles are deposited also matters. The particles are deposited, if you look at those figures here, there's a millions. Deposition, millions of particles are deposited in 1 minute. So I always keep asking my medical doctors, whom I collaborate, how we can survive. A million of particles a minute is ununderstandable. Okay, and they say, okay, but consider the area where are they deposited. The area of our lung is huge. Normally, somebody or students very often think that we are in contact with our environment, with our atmospheric environment through our skin. This is not true, because the human body is about 2 meters square, but our lung is 150 meters square. So as a matter of fact, the largest interface we are in contact with the environment is inside of our body, and this is called lung. So if we take into account the available surface area, and this is the smallest for the trachea. Trachea is a single tube. The main bronchi, if you add 2 bronchi, then they already represent larger area, and if you go deeper and deeper, the available surface area is larger. Therefore, this is the surface density deposition rate, shows you completely different pictures because the maxima are monotonically aligned, but the maxima happen in the second and the third airway generation, which means that most of the particles in the lung are deposited in the upper part. And this is extremely dangerous because the place or the location of the primary lung cancer is in the first and second generation, and the medical doctors say that it is related to air pollution. So if you consider primary lung cancer, it is from the upper parts, from the bronchi and the next generation, small bronchi. And if I summarize this part separately, then I would like to show you a healthy lung. Right lung, superior, middle, and the inferior lobe. And as I mentioned, if we integrate all their base, we obtain that 56% of the ultrafine particles are deposited in the lung. This is extremely large value. If we do the same modeling we did it before with the mass, deposition of mass in the lung, at most a few percent of the mass is deposited. So this is a very high value, surprising value. And we also figured out that in 1 minute, 1 million or 1 billion of particles are deposited. The particles are very small. So if you are to find them on the surface of the lung, you won't succeed because only a few particles are there. If you consider the total number, it is of course extreme. Most of the particles are deposited in the acinar region where the gas exchange takes place. And this is a real lung of a 67-year-old guy who lived and died in Budapest, and also he was a smoker. and you see the soot particles deposited in this line, and they are bending because of the ribbons. Okay, when you breathe, the ribbons drive the movement of the line, and the extremely large number and the black color of the soot particles visualize the deposition. So this is a picture which I show to my students very often because I'm very much against smoking. Of course, life is complex, and sometimes it is good to have a cigarette. Okay, as an aerosol scientist, you should know the risks. But let's be more serious again. And we also figured out that the physical activity is more important than the size distribution. So what you do is determining the deposition much more than in which part of the city of a region you are located. And the last issue that in the several 10-15 years ago, the medical doctors started to talk about effects of particles on cardiovascular disease, because the respiratory organs were affected and everybody was dealing with them. And decades, 15 years ago, they started to talk about cardiovascular diseases because the smallest particles can get through the cell membrane. They can get into the bloodstream, into the what is the other? No, I don't remember. Lymphatic system, and they change the physicochemical property of the blood. Okay, and they can cause coagulation, and immediately you are at the ischemic stroke. Okay, so cardiovascular diseases are influenced by ultrafine particles, and they are even smaller particles. They are called nanoparticles, which can get into the bloodstream and they are translocated. The translocation goes mainly to the central nervous system, to the brain, or to your liver. So these two organs are infected very much. And of course, I talked about the deposition in the lung, but if you consider the whole respiratory system, we can conclude that the maximum surface density deposition happens in the nose. And uptake from the nose takes place through smelling nerves and to olfactic nerves, which are connected not to our this part, but directly to the brain. Okay, so those nanoparticles through translocation can go directly to the brain, which represents a specific risk for the human health, because your brain is affected by nanoparticles. But at the same time, it also represents a beautiful challenge for therapy and identification of brain diseases. Okay, so this could be a new branch of aerosol science to have health implications of central nervous system. To cure the brain is, biologist. To cure the brain is very important because you have the lipid barrier.
The
Brain-blood barrier. And the medicines usually don't get, or they transport into.
Yes, the transport is strictly controlled by the accessory cells to the neurons. And so normally across the capillary there is a certain time of the transport of materials, solids, and so on. In this case, the cell, glial cells, to acquire the particles put inside, they can also process it and if they release the two neurons, neurons can acquire. It is a more controlled process than the absorption of normal solution, but it could happen as you.
And it depends on the lipophilicity of the molecules.
Yes, the lipophilicity of the molecules is a great parameter, is the most important parameters in controlling the diffusion. So in the case of nanometer, in the case, it depends on the size also and the composition of the particles. If the overall the particles is soluble, is lipophilic, it can be absorbed more easily to the membrane, and in the second way can be more easily phagocytated inside of the cell. For particle in nanometer diameters, simple diffusion across the plasma membrane does not simply occur. Simple diffusion of lipophilic particles more occur for more smaller lipophilic molecules. For particles, lipophilicity can help, but some active process of the cell in phagocytation, engulfation, and so on in the vesicular structure could be involved, but it is possible and it's very interesting. The connection, the direct connection from noise to the brain. Yes, it's very good.
Anyway, reaching the brain is very complicated, and this gives you a way, route, how to diagnose or how to cure diseases of the brain. So this could be important in the future. And of course, I talk to particle numbers as a metric of aerosol system, but some other metrics are also possible, like lung deposition surface area is also important. And I would like also to pay a very brief comment that in the lung we have almost 100% relative humidity. We start at 60, 70, and the particles, especially the smallest, the ultrafine particles, grow by hygroscopic growth. So the hygroscopic properties are also important. And to conclude, I was talking about atmospheric nucleation in Budapest, and the reasons we devote special attention to this, that nucleation is the major role of particles in the global atmosphere. I showed you that in cities in Budapest it is not marginal. It can be up to 30, 40%, so it's still considerable. And of course, 50% of the cloud condensation nuclei are generated by atmospheric nucleation. I also emphasize that we have 10 years of continuous measurements in the city center and one in the near city background. And the longer the data set, the more information you can extract of them. And I showed you that this is a regional phenomenon in the Carpathian Basin, and this gives a certain value of the results and conclusions. And that nucleation in cities has some specialty. And they include that the survival probability is different. The chemistry of the nucleation is not completely clarified. There could be some additional players. The quiet nucleation adds up on the role of nanoparticles and influences the urban air quality. As a new regulatory matrix of particle numbers could be, for instance, involved, and the respiratory deposition of ultrafine particles is also very important, which is related to urban air quality. I did not talk about the other objectives and other project of the BPR laboratory. We are active in secondary organic aerosols, CCM, hygroscopicity measurements, biomass burning, source apportionment. We do it very intensively recently, and some specific sources like fireworks. We just finished the work about the largest firework in Budapest, which has very detrimental effects on the person, also deposition. By the way, yesterday there was a firework in Lecce at the university campus. I don't know what to celebrate, but we recognize around after 9 there was fire. And of course, we have been started already, but one of my main purposes of the visit is to get some insight into the oxidation stress and oxidative potential. And I hope that we will be able to continue, and then we can help find another way to join our efforts. With this, I would like to thank, and I would like to show you the members of the BPR. If you are interested, all my publications are on my website, so you can find some details there. And I would like to acknowledge the members of the group. These two persons are employed half-time. These are two PhD students, and this is an engineer. It is also partly enrolled. So we have small group, only a few people. Some are changing all the time. And of course, it limits our possibilities and goals and whatever we have in mind and in plan. With this, I would like to thank your attention.
Okay, thank you very much. Even if you are a small group, you are doing a lot of things. See, we can stop the recording and go into the